You think a trip to Pluto is just a longer, colder version of going to Mars. Right, just stretch the timeline, add more shielding, bigger tanks, and you are done. You go there and you come back, that is the illusion. The hard truth is that the moment you decide to go to Pluto, with the tech we understand today, you are stepping out of the inner solar system in a way that makes a safe return in practice almost impossible. First, the basic layout. Earth orbits at 1 astronomical unit from the Sun, about 150 million kilometers, around 93 million miles. Pluto is not at 2 or 3 times that. It is at roughly 30 to 50 astronomical units from the Sun, depending on where it is in its stretched out orbit. That means you are talking about distances on the order of billions of kilometers, billions of miles. Even when Earth and Pluto line up in a good configuration, the separation is still around 4 to 7 billion kilometers, roughly 2.5 to 4.3 billion miles. Light itself takes hours to cross that gap. You are not just going to the edge of a map, you are stepping into a region where the map barely exists. So how bad is that in practical terms? Not just big numbers. Take something familiar, a normal passenger jet. A typical long-haul airliner cruises at around 900 kilometers per hour, roughly 560 miles per hour. At that speed, crossing 5 billion kilometers one way would take more than 600 years. Not 6, more than 600. That is for a single leg, not the round trip. Obviously you are not going to Pluto in an airliner, but this tells you how extreme the distance really is when you translate it into human time. Now look at one of the fastest objects we have actually flown, NASA's New Horizons probe. It left Earth at about 16 kilometers per second relative to the Sun, that is around 58,000 kilometers per hour, about 36,000 miles per hour. That is far beyond any airplane, beyond most other probes. And even with that speed, it still took about 9.5 years to reach Pluto, and it did not stop there. It flew past, grabbed its data during a brief flyby, and kept going. There was no braking burn, no orbit, no landing. The mission avoided the hardest part of the trip on purpose. Now ask yourself if that is what it takes for a small unmanned probe just to rush past Pluto once. What does it mean to send a heavy, crewed vehicle that must slow down enough to be safe, keep people alive, then later start up again and come back? You're not talking about a mission that fits into a presidential term or a single space program cycle. For the people on board, this is basically their entire working life, maybe more. The next problem is where Pluto sits in terms of how comfortable the solar system is for human operations. Inside about 2 astronomical units from the Sun, you can at least talk seriously about solar panels, reasonable communication times, resupply options, and rescue windows. You can imagine spare cargo ships catching up in a few months or a couple of years. You can use strong sunlight for power. You can design missions that can be adjusted if something goes wrong. Once you move beyond that region, things change. Sunlight drops with the square of the distance. Go out to 2 astronomical units, the light is down to 1/4 of what it is at Earth. Go to 10 astronomical units, you're at 100. Out by Pluto at roughly 30 to 50 astronomical units, the sunlight is around 1/900th to 1/1600th of Earth's. Solar panels that produce 1 kilowatt near Earth might give you around 1 watt out there. That is basically nothing for a human ship. Your usual energy and safety tools from the inner solar system stop working. That loss of comfort also hits your margin for error. Around Mars, if a mission slips, you might wait a couple of years for the next launch window. You might send a support craft, you might still have options. Around Pluto, once you commit to that transfer trajectory, there is no easy cancellation, no backup ship on standby, no quick way to send more fuel, more food or replacement parts. You press go, and you live with that choice for decades. Here is the part that really kills the idea of a Pluto round trip as just harder Mars. The difficulty does not scale in a straight line with distance. It does not go twice as far, twice as hard. Spaceflight is dominated by 2 things: how fast you need to go to change orbits, and how much energy you need to climb in and out of gravity wells, especially the Sun's. The farther out you go, the more your travel time and your energy costs blow up. And because rockets carry their fuel with them, all of that translates into mass. In rocketry, adding more speed, even just a few kilometers per second, is not cheap. You do not buy it with a few more tons of fuel, you buy it with a chain reaction. You add fuel for the final maneuver, then you need more fuel earlier in the mission to push that extra fuel. Then you need structural mass to hold all of that, plus more fuel to lift that extra structure. By the time you have enough capability to handle long-distance braking, course corrections, and a safe return burn from Pluto, your vehicle becomes enormous. Most of that size is just fuel to move more fuel. So when you push from Mars distances to Pluto distances, you're not just ramping up the numbers a bit. You enter a regime where every extra astronomical unit outwards multiplies the pressure on your design. Longer travel time, higher energy, more radiation exposure time, more life support, more things that can break, more fuel to move the added mass of all that protection. And if you want to come back, you have to pay that price twice, plus the cost to slow down at Pluto and the cost to slow down again when you finally reach Earth. This is why, with the engines and the materials we know how to build now, a human mission to Pluto is not just a long commute. It rips you away from everything that makes spaceflight barely manageable near the Sun. Distance, travel time and energy all gang up on you, and they do not just make the trip harder, they crush your safety margin until the idea of a guaranteed return starts to slip out of reach. So the natural next question is this. If covering the distance alone already stretches our best probes to the limit, what happens when you look closely at the speeds involved and you realise that getting to Pluto fast is actually the easy part, and that stopping, turning around and coming back is where the mission falls apart? How can getting to Pluto be called easy when the part that actually matters, stopping and coming home, is the thing that breaks the whole mission? New Horizons is the clearest example of this trap. It left Earth at about 16 kilometers per second relative to the Sun, around 58,000 kilometers per hour, about 36,000 miles per hour. But it only worked because the probe carried almost no fuel to slow down when it got there. The mission was built around a flyby, rush past, grab as much data as possible during a tiny window of minutes, then keep going into deep space. No braking, no orbit, no return. If New Horizons had needed to stop at Pluto to enter orbit, the design would have been different. It would have needed much more propellant, larger tanks, stronger structure, multiple heavy launches just to assemble it in Earth orbit. Engineers made a hard choice. You can reach Pluto fast, or you can arrive with the ability to stop, but you do not get both with a reasonably sized chemical rocket. So when people talk about humans flying there, going into orbit, landing, then coming home, remember, what we have actually done is a one-way, high-speed flyby with a robot that never hit the brakes. When you travel to Pluto on that kind of trajectory, you carry a large amount of kinetic energy, the energy of your motion. To get into orbit around Pluto or to land, you have to get rid of most of that speed. That means firing your engines in the opposite direction and burning for a long time, till your velocity drops from many kilometers per second down to the much lower speeds needed for capture or landing. That braking burn is not a minor tweak. It is on the same order as the energy you spent climbing out of Earth's gravity in the first place. You pay several kilometers per second of speed to leave Earth, then several more to slow down near Pluto. And rockets do not pay for speed in a friendly way. Each extra kilometer per second of velocity change eats dramatically more propellant. You add fuel, then you add more fuel to push that fuel, and very quickly the mass of your ship explodes. So when someone says, we just carry enough fuel to stop at Pluto, what that really means is, we bolt on another whole rocket stage whose main job is to hit the brakes. For a small probe, that is already painful. For a crewed ship, with habitats, life support, shielding, and all the other mass that humans need, that extra braking rocket becomes huge, and this is only the braking for the outbound leg. You still have the rest of the mission to pay for. Now scale up to a true round trip and list what your engines have to do. First, you accelerate away from Earth, spending a lot of energy to escape Earth's gravity and reach interplanetary speed. Second, when you arrive at Pluto, you brake hard enough to be captured, otherwise you just shoot past into the Kuiper Belt. Third, after your stay, you accelerate again, this time in the direction that sends you back toward the inner solar system. And finally, fourth, when you return to Earth, you slow down once more, either with a major engine burn or by hitting the atmosphere along a narrow corridor at about 11 kilometers per second, roughly 25,000 miles per hour. That is 4 large velocity changes, burns of several kilometers per second each. To put that into context, look at SpaceX's Falcon 9 first stage. Fully fueled at liftoff, it is around 400 metric tons, almost 900,000 pounds, and all of that mass only buys you a couple of kilometers per second of performance before it separates and falls away. A Pluto round trip is asking you to stack that level of energy again and again in one mission, with a vehicle that is not just engines and tanks, but also a human habitat that has to function for decades. This is where you feel how brutal the physics is. Every time you say, "we will just add the fuel for this burn," you quietly add more mass that makes every other burn harder. You cannot treat the 4 burns as separate problems. They are all locked together through the total mass of the ship. By the time you design a rocket that can launch, brake at Pluto, depart Pluto, and then brake again at Earth, your mass budget has blown up. Almost everything is propellant, almost nothing is payload, and that is before you bolt on shielding, redundancy, and life support. So you might say, fine, we will cheat with gravity assists, the way New Horizons use Jupiter. We will steal speed from giant planets and save fuel. That does help on the way out, when you can time your launch so that Earth, Jupiter, and Pluto line up in a useful pattern. You dive past Jupiter, let its gravity bend and boost your trajectory, and you pay less in propellant. But on the return leg, the game is worse. Pluto has moved along its 248-year orbit, Jupiter is somewhere else, and the alignments that helped you earlier may not exist on the schedule your life support allows. Your vehicle is older, its systems have aged, its engines have been used multiple times, its structure has taken stress for years. Now you are trying to hit gravity assist windows with a ship that is no longer fresh. Even if you do grab some assists on the way back, they do not erase the final braking problem. You still arrive near Earth with a huge amount of kinetic energy that must go somewhere. You must dump it as heat in the atmosphere or cancel it with engines. Gravity assists can bend your path and change your speed relative to the sun, but they cannot give you a free, perfect cancellation of all that motion right where you need it, safely for humans. That is the velocity trap. Getting up to Pluto crossing speed is, by itself, something we already know how to do for small machines. The part that kills the human round trip is everything that comes after. The braking at Pluto, the turn back inward, the braking at Earth, done with one massive vehicle that hauls its own fuel, life support, radiation shielding, and crew for decades. That is where the idea of a deep space road trip turns into a mission profile that, with chemical rockets and realistic engineering, is so close to impossible that nobody is funding it. And underneath all of these speed and fuel numbers, there is a deeper constraint, a mathematical rule that punishes every kilogram you try to carry. And it does not care how advanced your mission patch looks, so what happens when you ask that rule to approve a Pluto round trip? So why does one basic rule of rockets almost instantly kill the idea of a Pluto round trip, even before we talk about radiation or psychology? There is a simple relationship at the core of rocketry. It links 3 things: your engine performance, how much speed change you want, and how much of your rocket has to be propellant instead of useful stuff. The engine performance is basically how fast the exhaust shoots out the back. The speed change, the delta V, is how much you want to speed up or slow down over the whole mission. The mass ratio is how heavy the rocket is at the start with all the fuel versus how heavy it is when the tanks are empty. The ugly part is this: the relationship is not linear. It is exponential. In normal words, if you want a little more total speed change, you do not pay with a little more fuel, you pay with a lot more fuel. If you want twice the total delta V, you may need 3, 4, 10 times the propellant, depending on your engine. Very quickly, the rocket stops looking like a vehicle with some tanks, and starts looking like a stack of tanks with a tiny vehicle on top. For something like getting to low Earth orbit and maybe doing a bit more, the mass ratios are harsh but manageable. You might start at several hundred tons and end up with something like a few tens of tons in orbit. That is still painful, but it works. Now try to design a Pluto round trip. You are no longer aiming for maybe 9 or 10 kilometers per second of total delta V. Once you add Earth escape, course corrections, Pluto braking, Pluto departure and Earth return, you can easily end up needing something in the range of 20 to 30 kilometers per second in total. That pushes you deep into the exponential punishment zone. Your starting mass blows up into something absurd, and the useful payload, the part that actually holds humans, shrinks. Then the next problem hits. You do not just need fuel for your engines, you need fuel to carry more fuel. If you want to have enough propellant waiting for you at Pluto departure for the trip back, you must deliver that propellant there in the first place. That means the vehicle that leaves Earth is already loaded with outbound fuel plus return fuel. But loading that extra return fuel makes the outbound stage heavier, so you must add even more propellant just to push all of that off the launch pad and out of Earth's gravity. This is where you get the fuel for fuel spiral. It does not stop until your rocket stack is enormous. The Saturn V, the moon rocket, came in at about 3,000 metric tons at liftoff, around 110 meters tall, about 360 feet. And that was only to send a small crewed capsule and a lunar lander to the moon and back, with a total delta V far below what a Pluto expedition needs. If you try to scale that up for a Pluto round trip with chemical propulsion, the numbers suggest a vehicle that makes Saturn V look modest. Maybe multiple Saturn V class launches just to assemble one mission stack in orbit, maybe even a whole fleet of heavy lifters. And remember, Saturn V was mostly propellant already. We are talking about a system where the crew modules, the life support, the radiation shielding, the lander, and all the critical hardware are a small fraction sitting on top of layer after layer of fuel tanks and engines. Once you push the mission into the Pluto Delta V regime, that fraction shrinks even further, and the practicality drops. Now look at what chemical rockets can actually do. Modern chemical engines, burning liquid oxygen with hydrogen, methane, or kerosene, give exhaust velocities of only a few kilometers per second, roughly 2.5 to 4.5 kilometers per second, which matches specific impulses of a few hundred seconds. That is good for what we do now, launches to orbit, trips to the moon, Mars missions in the future. For those missions, you can design a stack where the total delta V, the total speed change, is in the single digits or low teens in kilometers per second, and the mass ratios, while harsh, are just about workable. A Pluto round trip does not live in that range. When you add up all the burns you need, you are not in a 9 or 12 kilometers per second problem. You can easily be in the 20 to 30 plus kilometers per second range if you want reasonable travel times and controlled arrivals and returns. In that band, chemical propulsion turns ugly. Your vehicle becomes almost all propellant, with a sliver of structure and payload. You can use chemical rockets to send a relatively small probe, with minimal payload and no return like New Horizons. But a full human habitat with radiation shielding, artificial gravity hardware, decades of life support capacity, and then enough propellant to bring that whole thing back, pushes you right against the wall of what chemical propulsion can deliver. So then the idea appears, fine, we will just refuel out there, we will make the return propellant at Pluto. On paper, this is called in situ resource utilization using local materials. Pluto has plenty of ices, nitrogen, methane, maybe carbon monoxide and other stuff. In theory, you land, you mine the ice, you split molecules, you chill and store propellants, and you launch home with full tanks. That sounds like a clean trick. You do not carry everything from Earth. You refuel like a car at a distant station. But that station is not simple. To do any of this, you need mining systems that can operate in temperatures around minus 230 degrees Celsius, about minus 380 degrees Fahrenheit. You need drills, excavators, storage tanks, plumbing, all designed to work in almost no atmosphere, with dust, with thermal stress for years. You need reactors or some other heavy power source, because out at 30 to 50 astronomical units. The sunlight is so weak that solar panels are almost useless. So now you're flying not just a spaceship, but a full industrial plant, with nuclear reactors, processing units and maintenance equipment. All of that has mass, big mass. It counts against you in the rocket equation on the way out. You have to lift every kilogram of mining gear, every reactor component, every pipe and valve out of Earth's gravity well and accelerate it all the way to Pluto. Then you have to slow it down there. The rocket equation does not care that this mass is helpful later. It just sees mass. And the more of it you carry, the more propellant you need, the higher your mass ratio gets, the bigger and more complex your launch architecture becomes. So just refuel at Pluto does not remove the fundamental limit. It moves the problem around and adds a huge new engineering burden. You still need a massive vehicle to deliver the fuel factory. You still need extreme reliability from those systems for decades. And if anything in that chain fails, your return ticket evaporates. You're stuck with a heavy, underpowered, partially broken industrial base in the dark, with no simple way for Earth to send replacement parts. This is why when mission designers run serious numbers for a crewed Pluto round trip with chemical rockets, the result is often not, "this is hard but doable," it is, "this is far beyond any sane mass and risk level." The exponential nature of the rocket rule is not a small detail. It is the thing that quietly closes the door. And it gets worse, because even if you somehow accept this crazy mass, even if you accept monster rockets, orbitals, shipyards, fuel depots, and nuclear mining plants on Pluto, you still have not solved another crucial piece. Pluto itself is small, its gravity is weak. Escaping its surface only takes about 1.2 kilometers per second. But the real killer is not the gravity at all. It is the orbit Pluto rides on around the Sun. How can a world with such weak gravity still be a trap? Not because of how hard it is to leave the surface, but because of the path it rides around the Sun. On paper, Pluto as a planet looks easy. Its surface gravity is only about 0.06 g, around 6% of Earth's. If you weigh 80 kilograms on Earth, you would feel like about 5 kilograms there. Its escape velocity, the speed you need to leave and never fall back, is roughly 1.2 kilometers per second, about 2,700 miles per hour. Compare that to Earth, where you need around 11.2 kilometers per second, about 25,000 miles per hour. From a simple gravity standpoint, Pluto looks like a small hill next to Earth's giant mountain. So at first glance you might think, fine, leaving Pluto is not the problem. You build a modest descent stage, nothing like a Saturn V, and you are off the surface with far less fuel. That part is true in isolation. The rocket that takes you from Pluto's ground up into space can be much smaller than the one that leaves Earth. The catch is, the main fight is not against Pluto's gravity at all. The main fight is against the motion Pluto already has around the Sun. Pluto is not just sitting there waiting for you, it is orbiting the Sun at about 4.7 kilometers per second, around 10,500 miles per hour. When you arrive at Pluto and want to land or orbit, you cannot just dive straight in from some random direction. You must match that orbital motion closely, or you will shoot past at high speed. That means a huge part of your trip is spent bending and tuning your path so that when you cross Pluto's orbit, your velocity relative to Pluto is low enough that you can actually stop and stay. Then, when you want to come back, you are starting from Pluto's orbit, far out in the solar system, moving at that modest 4.7 kilometers per second around the Sun. Earth is down in the inner system, much closer to the Sun, orbiting at about 30 kilometers per second, roughly 67,000 miles per hour. To return, you have to completely reshape your path, trading one orbit for another, dropping down the Sun's gravity well and speeding up dramatically. This is not just push off Pluto and fall inward. You need a carefully timed maneuver that changes your speed and direction by several kilometers per second, just to get on a trajectory that will meet Earth again at the right time and place. In simple terms, Pluto's weak local gravity tempts you into thinking it is a soft target. But the orbital energy, the energy of its path around the Sun, is huge. It is like being on a moving walkway that is very slow compared to Earth's, but extremely far from the center of the room. To get back to the fast inner track, you must pay a big speed change, either at Pluto, on the way in, on the way out, or some combination. That cost in propellant and timing is what really bites. There is another layer. Pluto's orbit is not nice and flat like Earth's. The inner planets all orbit roughly in the same plane, the ecliptic. Pluto's orbit is tilted by about 17 degrees relative to that plane, and it is also very stretched, very eccentric. Sometimes Pluto is closer in, sometimes much farther out. That tilt and stretching complicate your trajectory in a way Mars and Jupiter do not. If your approach path does not already line up with Pluto's orbital plane, you must rotate your orbital plane to match it. That kind of sideways adjustment, a plane change, is one of the most expensive maneuvers you can do in orbital mechanics, especially when your speed is high. At Pluto's orbital speed of about 4.7 kilometers per second, even a modest plane change can cost on the order of 1 to 2 kilometers per second of extra delta V. That is not a small tweak. That is another major burn with all the fuel penalties that come with it. So say you design a mission that tries to minimize that by accepting awkward timing or long travel times. You still end up paying in some way, either more time or more speed change. And all of this feeds straight back into the rocket equation problem you just saw. Every extra kilometer per second you need for plane changes or orbital reshaping means bigger fuel tanks, heavier structures, and more launches to assemble the stack. Pluto's weird orbit forces you into a corner where you pay in complexity, mass, or both. Then comes the timing nightmare on the way back. Pluto takes about 248 years to go around the Sun once. While your spacecraft is crawling through space over decades, Pluto is moving along that long, tilted, stretched out path. The geometry you had when you arrived will not be the geometry you have when you're ready to leave. Departure is not just reverse the burn and go home. For a fuel-efficient return, you want specific alignments between Pluto, the Sun, Earth, and maybe other planets for gravity assists. Those alignments do not happen whenever you feel ready. They happen on their own schedule. If your systems are aging, your supplies are limited, and your crew cannot wait indefinitely, missing an optimal departure window can mean you either accept a much longer, slower trajectory, or you spend extra delta V to force a faster path. Both options are bad. Longer time means more wear, more radiation, more life support strain. More delta V means more fuel you probably do not have. So suddenly, your round trip is not a clean out and back. It starts to look like a multi-decade chess game in 4 dimensions, where the pieces never stop moving. You have Earth racing along at 30 kilometers per second on the inside track, Pluto crawling far out with its 17-degree tilt, Jupiter and Saturn sliding around offering gravity assists at certain times, and your ship, which must hit narrow windows with almost no slack. And while that is happening, your engines age, your power systems degrade, your crew gets older, and your margin for error shrinks. This is why when you think about Pluto as a place to visit and then leave, you cannot just look at its weak gravity and say easy escape. The real escape problem is escaping the position and motion Pluto has in the solar system. You pay for that in velocity changes, in plane changes, in long waits for launch windows. All of that pulls your mission deeper into the same mass and fuel spiral that was already nearly impossible. And then you stack one more brutal fact on top, even if you somehow beat the orbit puzzle. Even if you accept the complex maneuvers and the long alignments, the clock does not stop for you. Travel times stretch into decades. Human bodies and minds are not built for 20, 30, 40 years in transit with no real way to go home early. So if the orbital mechanics already look hostile, what happens when you match those timelines against the length of human life? How do you call something a mission when, in practical human terms, it eats most of a lifetime just to go there and come back once? Take the best speed we have actually used to reach Pluto New Horizons levels. That probe took about 9.5 years to go from Earth to a fast flyby. That was with a very light spacecraft, no people, minimal shielding, and no need to slow down. If you want to carry humans and you want to arrive safely enough to enter orbit or land, you cannot just slam past Pluto at that speed. You have to arrive slower, which means your trajectory is less aggressive or you spend more energy braking, and both of those make the travel time longer. So even if you somehow match that 9 to 10 year outbound time with a crewed ship, you're still talking about roughly a decade one way. More realistically, if you trade some speed for safety, your outbound leg could be 12, 15, maybe more years. This is not the Mars profile where you talk about a few months outbound, a stay of maybe a year or two and a few months back. A Pluto mission means you commit most of your working life just to getting there before you even start the return sequence. Now stack the rest of the path on top of that. Whatever time you spend going out, you have to expect something similar, or worse, coming back. Call it 10 years to Pluto, 10 years back, that is 20 years already. Add time for breaking into Pluto orbit or landing, time for surface operations or orbital research, time waiting for a decent transfer window to head home, and time lost to less than perfect alignment. You're easily in the 25 to 40 year range for a full round trip that does not push every parameter to the edge of disaster. If you launch in your early 30s, you could be seeing Earth again in your late 50s, 60s, maybe even 70s. That is assuming nothing major goes wrong, your ship holds together, your power systems survive, your medical systems perform, and you personally do not suffer a career-ending health issue. From a calendar perspective, this is not a mission, it is almost an entire adult life spent off-world. Human biology is not designed for that kind of exile. We already see serious problems in low Earth orbit, just a few hundred kilometers up, on missions lasting months. On the International Space Station, in microgravity, astronauts lose bone density, their bones thin out, muscles weaken and shrink. The cardiovascular system adapts to a world without normal G and then struggles when they come back. The immune system changes, eyes can be affected. That is in an environment with constant medical monitoring, resupply flights every few months, and the option to return to Earth in hours if needed. Now, scale the time from months to decades. Even if you solve part of the problem with artificial gravity by spinning a habitat to simulate 1G, or something close to it, you still have long-term issues. Radiation exposure accumulates, micrometeorite risk accumulates, mechanical wear on your centrifuge system accumulates. You would need a closed life support system running reliably for decades, plus regular heavy exercise and medical care, just to keep the crew from degrading too far physically. That is a space station level challenge multiplied by a factor of 10 or 20 in duration. And the body is only half of the story. The mind has to survive this too. On Earth, people stationed in Antarctic research bases show stress, depression, and conflict. And they know that rescue is weeks away and communication is fast. Submariners operate in confined spaces for months, but they can surface, they have oxygen from the planet, and they can be extracted in emergencies. These are still hard environments, and people still crack under the pressure. At Pluto distances, communication itself stretches out. Radio signals travel at the speed of light, but the distance is so huge that even light takes a long time. Depending on the positions of Earth and Pluto, a message can take roughly 4 to 7 hours to go one way. A question and answer exchange can eat most of a working day. There is no real-time conversation with mission control, no quick call home, no live video chat. If something goes wrong, you send a report, wait hours, get suggestions, and then see if those suggestions are still relevant to the situation by the time they arrive. On top of that, there is no realistic rescue. If hardware fails in some deep mission-critical way halfway to Pluto, there is no second ship on standby that can catch up. The distances and timescales are too big. You cannot send spare parts by express delivery. The crew knows, at a deep level, that from the moment they leave Earth orbit, they are on their own system, and that system has to work for decades or they die. That is a very different psychological load compared to a 6-month station mission or even a multi-year Mars program. Over a 25 to 40-year timeline, you expect normal human life events. People age, relationships on Earth change, parents die, children grow up. The crew has to process all of that from billions of kilometers away, with huge delays, and no way to go back early to attend anything or see anyone. For many of them, by the end of the mission, everyone they left behind will be older by an entire generation. Coming home would not feel like returning from a deployment. It would feel like stepping into a future where you have been missing for decades. Now combine that with the operational demands. You're not just surviving, you're doing complex work, maintaining systems, running science, performing navigation checks, dealing with anomalies. You cannot afford a crew where half the members are physically weakened and psychologically exhausted past the point of being effective. Yet realistically, the chances that every single person who leaves Earth is still mentally sharp, physically capable, and emotionally stable 30 years later after continuous deep space stress are not high. This mismatch between mission length and human capacity is one of the reasons people quietly shift Pluto missions from round trip to one-way in practice. You can design a spacecraft, at least on paper, that might handle decades if you throw enough mass, redundancy, and engineering at it. But designing human minds and bodies that stay fully mission-ready under those conditions, without any way to rotate crews or send replacements, is a different challenge. We simply do not have anything close to real data on that scale, and there is a final twist. The longer the mission, the more pressure there is on every other system. Life support must run longer, reactors must output stable power longer, engines must remain reliable longer, computers must resist radiation longer. Travel time and human lifespan are not just a medical problem, they amplify every other risk. The longer the mission, the more chances something breaks that you cannot fix. So even if you accept the brutal distances, the high speeds, the rocket equation, and Pluto's awkward orbit, you still run into the question that does not go away. How do you keep humans alive, healthy and sane in a metal shell for most of a lifetime? And if you cannot answer that with high confidence, what happens when you remember that all of this has to run in a place where sunlight is almost gone, and your entire survival depends on power systems that cannot fail? How do you run a ship for decades in a place where the sun has basically been turned down to a distant cold star, and still expect to have enough power left to come home? Near Earth, solar power feels easy. At 1 astronomical unit, the sunlight is strong, about 1,360 watts per square meter at the top of the atmosphere. You stick panels on a satellite, you get kilowatts without thinking too hard. But the intensity of sunlight drops with the square of the distance. Double the distance, you get only 1/4 of the light. By the time you're out near Pluto, roughly 30 to 40 astronomical units from the Sun, you are down to somewhere between about 1/900th and 1/1600th of Earth's sunlight. Put numbers on that. Take a solar panel that near Earth gives you 1 kilowatt of power, enough to run a small heater or a microwave. Drag that same panel out to Pluto's orbit. Now, instead of 1,000 watts, you're getting about 1 to maybe 1.5 watts. That is barely enough to run a small LED flashlight. To replace even a modest power system that gives you tens of kilowatts, you would need arrays spread over areas measured in football fields, not rooftops. Each field-sized array would have to be built, launched from Earth, unfolded in space, pointed accurately, and then kept working for 30 or 40 years through micrometeoroids, thermal stress, and mechanical fatigue. On top of that, a human ship is not a static satellite. It has to maneuver, rotate, maybe spin to create artificial gravity. Huge arrays make that harder. They add mass, they add drag from the tiny dust and particles in space, and they can snap or twist under even small forces. The complexity goes up, the failure modes multiply, and for what? A few kilowatts in deep space if you're lucky. For a Pluto mission that has to work for decades, solar panels stop being your main power source and start being almost dead weight. So you move to what we already use for deep space, radioisotope power. Probes like Voyager and New Horizons rely on radioisotope thermoelectric generators, RTGs. They carry a small amount of plutonium-238. As it decays, it releases heat, and thermoelectric devices convert some of that heat into electricity. No moving parts, extremely reliable, and they do not care how far from the sun you are, which is perfect for the outer solar system. But look at the scale. A classic RTG outputs only a few hundred watts of electric power at the start, and that power slowly drops over time as the plutonium decays. That is plenty for a robotic probe with a few instruments and a transmitter. A human ship is different. You need tens of kilowatts, maybe hundreds, to run life support, navigation, communications, computers, lighting, environmental control, and maybe electric propulsion systems. To reach those levels using RTGs, you would need many units, and that means a lot of plutonium-238, which is rare, expensive, and sensitive. You are now talking about flying tons of nuclear material just for the power, before you even think about propulsion fuel. And even if you accept that, RTGs still fade over time. On a 30-plus year mission, your available power will steadily decline. Systems that were comfortable at the start become power-starved near the end, which is exactly when you need everything to work perfectly for the return burns and the Earth approach. The next step up is small fission reactors, nuclear reactors in space. Instead of relying on decay heat, you run a controlled chain reaction, like a tiny continuous power plant. Now you can generate tens or hundreds of kilowatts from a relatively compact unit. This looks like the only realistic way to power a serious crewed mission in the Kuiper Belt region. But now look at what you're asking that reactor to do. It has to run essentially unattended for 30 years or more, with no refueling, no replacement of key components, in an environment where outside temperatures hover around minus 230 degrees Celsius, roughly minus 380 degrees Fahrenheit. The ship is bombarded by cosmic rays and solar particles, electronics age, materials become brittle, and every weld, pipe and control system must survive. Submarine reactors on Earth get regular inspections, overhauls and refits. If something looks off, you bring the boat into dock. A space reactor on a Pluto mission does not get dock time. If it starts to drift out of spec, you fix it with whatever tools and spare parts you brought on day one. If it fails completely, you lose power. A failure of your main power system on the outbound leg is basically a death sentence. Life support stops, pumps and fans shut down, heaters die, guidance becomes unreliable. If you are already near Pluto and the reactor fails there, you might have some emergency batteries or backup RTGs, but those will not be enough to run full systems or power major engine burns. You would be alive for a while sitting in the dark, but the ability to command your return trajectory evaporates. This is the part people often miss. Power is your hidden return ticket. You can do all the math you want on delta V, fuel and mass ratios, but none of it matters if, at the moment, you need to start your engines for the trip home. Your power budget is not there. Engines need pumps and valves need actuators need controllers need computers need stable electricity and thermal management. Your communication array needs power to send telemetry and receive updated instructions. Your attitude control, your reaction wheels, your thrusters all feed off that same electrical backbone. If your reactor has degraded more than you planned, or your RTGs have decayed faster, or your solar arrays have been damaged by dust impacts or mechanical failures, your ship might still technically have propellant in its tanks and engines that work on paper, but you cannot safely operate them. You cannot run the full sequence of burns, you cannot keep guidance online while the engine is firing, you cannot maintain thermal control while heaters and pumps compete for limited watts. The return sequence is not just risky, it becomes physically uncommandable. The ship is there, the fuel is there, but the electrical muscle to control it is gone. Notice how this connects back to everything else. To increase safety, you want more redundancy in power systems, more backup reactors or RTGs, more batteries, more wiring, more shielding. All of that adds mass, which makes the rocket equation worse, which makes the mission longer, which demands more from your power systems over time. It is a loop. The farther you go, the more you need power to stay alive, and the longer you have to trust that power not to fail. And this leads directly into the next nightmare. Power is not the only thing that must work for decades. Every system that keeps you breathing, drinking, eating and safe has to survive just as long. If the power system is your hidden return ticket, life support is the thing that decides whether you even live long enough to try and use that ticket. So what happens when you ask a closed life support system not to run for months or a couple of years, but for half a human lifetime, with no resupply and no real chance to repair it properly? How do you keep 4 people breathing, drinking, and eating for decades in deep space without turning the entire mission into one giant stack of food and water tanks that can never leave Earth? Start with simple numbers. A human needs on the order of a few kilograms of stuff every day, water plus food. Take a rough but reasonable figure, around 5 kilograms per person per day. Counting drinking water, water and food, and the food itself. Now scale that to a small crew, say 4 astronauts. That is 20 kilograms every single day. Stretch that over 10,000 days, which is about 27 years, and you end up with around 200,000 kilograms of consumables, 200 metric tons just in food and water before you recycle anything. In imperial terms, that is more than 440,000 pounds, more mass than an entire fully fueled Apollo Saturn 4NYB rocket on the pad. And remember, that is lowball. It does not include packaging, storage tanks, losses, or any safety margin. If you actually tried to carry all of that from Earth as a one-shot stockpile, your mission is dead before it starts, because the rocket equation will crush you. 200 tons is already a huge launch, and that is only the consumables, not the structure, engines, shielding, fuel, or equipment. So you have no choice. You must recycle almost everything, and you must do it for an absurdly long time. We do know how to recycle some things, for a while. On the International Space Station, water gets recycled aggressively. Urine and humidity in the air are processed back into drinkable water. Carbon dioxide is scrubbed from the air and oxygen is added back in. That system works, but it still needs spare parts and resupply, and it has not been asked to run perfectly for decades without help. On Earth, there have been experiments like BIOS 3 in Russia and Biosphere 2 in the United States, closed ecosystems where plants, water systems, and people had to balance each other. Even there, with full gravity, nearby support, and the option to truck in emergency supplies, those systems struggled. They had issues with oxygen levels, trace gases, and keeping this balance stable. Now move that problem into deep space. You're running a closed-loop life support system in microgravity, or in a spinning artificial gravity habitat under constant radiation, with no outside air, no outside water, and no real way to dump waste except into your own processing systems. There is no resupply capsule. There is no maintenance crew from Earth coming up to swap out a failing unit. Everything that fails has to be repaired with the tools and spare parts that left Earth with you years ago. That pushes you into heavy redundancy. You cannot fly a single carbon dioxide scrubber and say, it will be fine. If that one unit fails, everyone dies. So you need at least 2. Then you realise the backup can also fail, maybe for the same reason. So you add a third, maybe a fourth, maybe different types of scrubbers to avoid a single common failure mode. The same thing happens with oxygen generators, water recycling units, sewage processors, air circulation fans, and any biological systems like greenhouses or algae bioreactors. Every time you add redundancy, you add mass. Multiple oxygen generators, multiple waste processors, multiple hydroponic systems, backup pipes, extra pumps, spare sensors, extra wiring. The structure to hold them, the shielding to protect them, all of that stacks up. Each ton you add to make life support safer on year 25 of the mission makes your launch stacks bigger, makes your fuel demands higher, and makes your propulsion problem harder both on the outbound and the return journey. There is no free safety. Every layer of just in case feeds directly into the rocket equation nightmare you already have. And then there is the slow, constant attack from basic physics and biology. Entropy, filters clog, seals get brittle and leak, bearings wear out in pumps and fans, microbes grow where you do not want them, slimy biofilms in pipes, mold in corners, bacteria in filters. Plastics slowly release gases, changing the air mix. Metal can corrode even in controlled environments, especially if there is moisture and trace chemicals around. Electronics, sensors, circuit boards, all age under radiation and thermal cycling. On the ISS, when a filter clogs or a pump fails, you send up a new one on the next cargo flight. If a system starts acting weird, you can replace the entire unit. The station is close enough to Earth that hardware fatigue is a solvable problem. On a Pluto ship, your nearest spare part warehouse is billions of kilometers away. Every filter you will ever use, every pump, every pipe section, every motor, every bag of replacement growing media for your greenhouse, all of it has to be there on day one, or you'll not have it at all. Designing a life support system for 2 to 3 years is already hard. That is the level people discuss for Mars, and it is full of risk. Stretch that requirement to 30 years, plus large safety margins, and you are no longer building a spacecraft in the normal sense. You're building a travelling city with its own water plant, air plant, sewage treatment, food production, waste management, hospital, and repair workshop, all crammed into a finite volume that has to survive the stresses of launch, deep space flight, and distant operations. That city has to be closed. It cannot dump waste overboard freely, because anything you throw away is mass you no longer have to recycle into something useful. It cannot rely on outside deliveries. It cannot shut down big sections for maintenance while people move to a different building. Everything has to keep running while you are using it, while you are living in it. You also have to think about how robust your biological systems are over that time. If you grow food on board, you're running a farm in space, crops will mutate slowly. Microbial communities in your soil or hydroponic systems will shift. Pests or diseases can show up in your closed ecosystem, and you cannot spray the field and start over easily. You cannot just go buy new seeds if a key plant strain fails. If your farming system crashes in year 18 of a 35-year mission, you need to have enough backups and stored food to survive a long recovery, or you die. You might say, fine, we will keep it simple and carry a huge stockpile of dried food and only recycle water and air. But go back to the mass numbers. Even with partial recycling, a decades-long mission for 4 or more people is still going to demand many tens of tons of consumables. And you still need redundancy in water systems, air systems, and waste handling. You're not getting away from heavy, complex life support. You are just shifting where the complexity lives. All of this brings you to a brutal conclusion. Life support for a Pluto round trip is not an add-on. It is the main payload, in volume, in mass, and in engineering difficulty. The ship you end up drawing is overwhelmingly a life support and habitat structure, wrapped around a power plant and strapped to a propulsion system that itself has to be enormous just to move this floating city out and back. And there is still one more layer of pain, because even if you accept the size and the mass and the complexity, you then have to ask, can that whole machine with all of its moving parts, electronics, bearings, seals and computers stay reliable for 30 or 40 years in deep space when even our simplest probes start to fail under that kind of timeline? How do you trust a machine with your life when it has to run longer than most people's entire careers, with no chance to shut it down, rebuild it, and start fresh? Everyone points to Voyager 1 and Voyager 2 as proof that long missions are possible. They launched in 1977, they have been out there for roughly 50 years, and they are still sending data. On the surface, that sounds like a green light for a Pluto round trip. But look closer at what that really means. The Voyagers are simple compared to what a human ship would be. Each one is a bus-sized probe with fixed antennas, a small number of instruments, and a handful of thrusters. Over time, they have steadily lost instruments, cameras, and subsystems. Their power has been dropping as their RTGs decay. Engineers constantly have to shut things off to keep the essentials alive. They have had glitches, they have had memory issues, they have had communication problems, and all of that is on a platform that does not need to keep people breathing or warm. So yes, they are incredible success stories, but they're also warnings. Even with very simple hardware, designed to be rugged, with minimal moving parts and no human life attached, staying operational for decades in deep space has been hard. Components fail, power runs out, software has to be reconfigured to work around damage. Now scale that up to a ship that is not a few hundred kilograms but hundreds of tons. A crewed Pluto vehicle is the opposite of simple. You're packing it with pumps for fluids, compressors for air, rotating habitats for artificial gravity, airlocks that cycle constantly, toilets and waste processors, plant growth systems, water recycling units, radiators, docking ports, and maybe centrifuges or moving boom arms. Instead of a few scientific instruments that you can afford to lose, you have an entire city's worth of systems that must work, not just to gather data, but to keep everyone alive. Every pump has bearings that can wear. Every valve has seals that can harden or crack. Every rotating joint can lose lubrication. Every spinning habitat or centrifuge has motors and structural elements under constant stress, going through billions of tiny vibrations and temperature swings over the course of 30 or 40 years. Even if each individual component has a very low chance of failing per year, the total number of components is so low that statistically things will break. The question is not if, it is how many, how often, and can you fix them with what you brought? Then there is the electronics, which do not just sit there peacefully. Deep space is full of radiation, from cosmic rays and solar high-energy particles. When those particles hit microelectronics, they can flip bits in memory, they can cause single-event upsets, they can temporarily or permanently lock up chips, they can slowly degrade materials inside the devices. Radiation-hardened chips exist, but they are slower, bulkier, and less power-efficient than modern consumer processors. You cannot just bolt a gaming CPU into a Pluto ship and expect it to survive 30 years of cosmic exposure. Over decades, these radiation hits accumulate. You get more and more random errors, more glitches, more corrupt data. To protect against that, you need multiple redundant computers, not just one main flight computer. You need error-correcting memory, so that when bits flip, the system can detect and fix them. You need software that cross-checks results between processors, so that if one unit starts acting strange, the others can outvote it and keep the ship on course. All of that adds mass and complexity. Extra computers, extra memory, extra wiring, extra shielding, and extra testing. You're building a flying data center that has to be trustworthy for an entire generation, and you cannot power cycle it like a laptop when something feels off. And remember, this electronic backbone has to stay reliable not only for navigation, but also for controlling engines, life support, power management, and communications. A single bad failure in the wrong controller at the wrong time can ruin a critical burn or shut down an essential system. Now think about spare parts. On Earth, any industrial plant that is 30 years old has gone through constant maintenance. Pumps, motors, valves, control panels, all of it gets swapped out, upgraded, repaired. Parts wear out, new designs replace old ones, entire subsystems get rebuilt or retired. Even nuclear plants get major refits. Nobody expects a complex mechanical system to just run untouched for 3 decades. A Pluto ship, if it is going to be honest about survival, has to carry every spare up front. That means spare pumps, spare fans, spare circuit boards, spare sensors, spare screens, spare capacitors, spare pipes, spare seals, spare wiring harnesses, spare bearings, maybe even spare segments of rotating habitats. You're not just flying a spacecraft, you're flying your own machine shop with tools and raw materials to fabricate repairs you did not fully foresee. You need test gear to diagnose faults, you need storage for all of that. Every extra lifeboat you add, every backup avionics box, every emergency battery bank, every duplicate communication antenna, all the extra hardware you bring just in case feeds straight back into your mass budget. More mass means more fuel to launch. More fuel to launch means bigger rockets. Bigger rockets mean more complexity and cost. And more complexity means more things that can fail even before you leave Earth orbit. You can try to be clever and say, we will design ultra-reliable, super simple systems, but a human mission to Pluto cannot be truly simple. You need complexity to handle healthcare, comfort, stability, recycling, farming, scientific work, and operations for decades. You can try to lower the number of moving parts, but there is a floor you cannot cross and still call it a humane, survivable environment. The Voyagers show that with careful design, minimal moving parts, and a lot of luck and ground support, you can get a machine to limp along for half a century, but even they are fading out as power drops and systems fail. A crewed Pluto mission would start out much more complex, under harsher requirements, with far less tolerance for failure. You do not get to say, well, that instrument is dead, but the mission can sort of continue. If certain systems die on a crewed ship, people suffocate, freeze, or drift off course forever. So even before we talk about landing, or takeoff from Pluto, or the final re-entry to Earth, the reliability problem is already whispering in the background. How do you trust thousands of interconnected parts under radiation and thermal stress? Not just for a few years, but for 30 or 40. And if you cannot, what do you do about the one deep space enemy you can never fully shield against? The constant rain of radiation and cosmic rays that, over decades, starts turning your ship into a slow, invisible health hazard for everyone on board? How do you send people into deep space for 30 years when the space between here and Pluto is basically a slow, invisible radiation bath that never turns off? Once you leave Earth's magnetic field, you lose your main shield. Out there, you are sitting in a constant stream of galactic cosmic rays and bursts of solar energetic particles. On the International Space Station, astronauts get a few hundred millisieverts of radiation dose over about 6 months. That is already enough that space agencies track their lifetime dose and limit how often they fly. Now stretch that out, not for 6 months, but for 20 to 30 years. Even if you add some reasonable shielding, you're talking about total doses in the multiple sievert range, maybe several sieverts or more over a full mission. At those levels, you're not just slightly increasing cancer risk. You're pushing crew members into serious territory, where the probability of major health problems, cancers, and degenerative diseases becomes very high. Over decades, radiation also attacks blood vessels, the brain, and other organs. This is not a you might get sick in your 80s thing. This can be disability or life-shortening disease while the mission is still going. So you say, fine, we will shield the ship. But shielding is not a free slider you can just turn up. The particles you really care about, especially galactic cosmic rays, are extremely energetic. To cut their dose significantly, you need thick layers of material. Hydrogen-rich stuff works best. Things like water or polyethylene, because they slow down incoming particles without creating too much secondary radiation. Metal works too, but you need several centimeters of it, and heavy metals can actually produce showers of secondary particles when hit. If you want to build a spinning habitat, say a big ring that simulates 1G or some fraction of it, and you want to wrap that in tens of centimeters of shielding all the way around, your mass explodes. You're easily talking hundreds of tons of extra material just for radiation protection around the living zones. That is on top of the structure, life support, food, water engines, and everything else. Every ton of shielding you add has to be launched from Earth. It has to be pushed out of Earth's gravity well, accelerated toward a Pluto, slowed down there, and then accelerated again to come back. That feeds directly into the rocket equation nightmare. More shielding means more fuel means a bigger vehicle means even more fuel, and you are back in the loop where the rocket becomes mostly propellant. And that is just the steady background. On top of that, you have solar storms, the sudden spikes. The sun sometimes throws off huge flares and coronal mass ejections, massive blasts of charged particles. A really big event, like the 1859 Carrington event, could deliver a dangerous or even lethal dose to an unshielded crew in hours. Inside Earth's magnetosphere, those storms are mostly a power grid problem. Outside, they can be a direct threat to human life, so you need a storm shelter built into the ship, a place where the crew can retreat when instruments see a big solar event coming. That shelter has to be heavily shielded, much more so than the rest of the living space. In practice, that means surrounding a central room with thick water tanks, food stores, and dedicated shielding materials. It has to be big enough for the whole crew to stay there comfortably for hours or days. It has to be close to critical controls so you can still operate the ship safely while you wait out the storm. Again, that is extra mass, extra complexity, and extra design constraints on where you place life support, controls, and power systems. You cannot just put the shelter anywhere. You have to integrate it into the ship's core, where geometry and structural loads make sense. And remember, this is on top of your normal shielding for day-to-day radiation. You might say on a short mission, we accept some risk. For something like a Mars trip, you can argue that the exposure, while serious, might still be within what we can tolerate. at least for a few carefully selected crews. You roll the dice on a couple of years in deep space. If the sun is relatively quiet, if you get lucky with storms, and if your shielding is decent, the long-term health hit, while real, might still be acceptable to agencies and astronauts. But a Pluto round trip is not a short mission. You're not talking about 1 or 2 years outside the magnetosphere. You're talking about 20, 30, maybe 40 years of exposure. Even if your shielding is good, the dose just keeps adding up. Galactic cosmic rays do not stop, solar particles do not stop. You have more time for big storms to hit. You have more time for rare, high-energy events to show up. Over that kind of timescale, the cumulative probability that at least one crew member develops a serious radiation-related condition becomes very high. Cancers, cardiovascular disease, neurological effects, all of it. The mission design might still say, yes, it is physically possible to fly there and back, the equations allow it. But human biology quietly says, you're almost guaranteeing that someone pays a heavy price. And if you try to drive the risk down by adding massive shielding, you hit the mass wall and the rocket equation again. If you try to accept less shielding, you hit the health wall. There is no solution that is both safe for a multi-decade human mission and compatible with what chemical rockets can reasonably lift. So even if you imagine we somehow build a ship that can run for 30 plus years without falling apart, life fuel support that recycles perfectly and enough power to keep everything alive in the dark, you still have this invisible constant enemy that you cannot see and cannot turn off, slowly eating away at both the crew's bodies and the electronics that guide them. And that brings up another sharp question. Even if everyone on board stays healthy enough, and even if the hardware stays just functional enough, what happens if your navigation drifts just a tiny bit, over 5 billion kilometers, and you discover that being off by a fraction of a degree means missing Earth completely when you try to come home? How do you aim at a moving planet from billions of kilometers away, knowing that a mistake smaller than a hair's width in your pointing angle can turn "we're home" into "we missed the entire world"? When you throw a spacecraft toward Pluto and then back to Earth, your path is incredibly sensitive to tiny errors. Take one number, a 1 microradian pointing error. That is a tiny angle, about 1/1,000,000th of a radian, so small it is hard to visualize. Over a distance of 5 billion kilometers, that tiny angular slip grows into about 5,000 kilometers of positional error, more than 3,000 miles. That is about the size of a small planet. So a guidance error that looks microscopic on your instrument readout can mean your return trajectory passes thousands of kilometers away from where Earth actually will be. Because of that, you cannot just burn the engines once and coast blindly. You need repeated, precise course corrections all the way out and all the way back. You update your position using radio tracking, star trackers, maybe optical navigation on planets or stars. And then you do small burns to nudge the path back toward the ideal line. That process never really stops. For a mission that spans 20 to 30 years, you're talking about course checks and corrections over and over as everything slowly drifts. Each one of those corrections costs propellant. It might be a tiny burst from a thruster, just a few seconds at a very low thrust, but it still eats into your Delta V budget. Missions like Cassini and New Horizons use small but non-zero burns throughout their journeys to stay on track and hit their flyby targets. Over a decade, those small burns add up. Over 20 or 30 years, they add up even more. So if you under-budget your correction fuel, or if your ship ends up needing more corrections than planned because the sensors age or the environment is harsher than expected, the error can grow beyond what you can fix. By the time you're approaching the inner solar system again, the accumulated drift might be too large to cancel with the fuel you have left. The result is brutal. You arrive near Earth's orbit, but your path misses the planet by tens of thousands of kilometers. Close in astronomical terms, useless in practical terms. Now ask what is doing the measuring for all of this. Your navigation depends on hardware, star trackers that look at the sky and identify known stars, gyroscopes that track rotation, reaction wheels that help point to the ship. None of these parts are immortal. Star trackers use detectors that slowly get noisier as radiation damage accumulates. Dead pixels show up, sensitivity drops, gyros have drift, small errors that build up over time if you do not reset them with external references. Bearings in reaction wheels wear down. Lubrication breaks down, wheels can fail completely and have to be shut off. So while your need for precision goes up as you approach Earth for re-entry, your tools for measuring your attitude and position are getting worse. They are literally aging in the dark. You can design in redundancy, multiple trackers, extra gyros, extra wheels, but we are back to the same theme. Redundancy adds mass adds fuel adds launch complexity, and over a 30-year mission, even redundant systems can reach end of life. You might be trying to thread the most important needle in your entire flight with sensors that are well past their original design lifetime. All of this funnels down into a final, unforgiving requirement. Coming home does not just mean hit Earth's general area. You must hit a narrow re-entry corridor in the atmosphere at around 11 kilometers per second, about 25,000 miles per hour. Too shallow and you skip off the upper atmosphere and go back out into space on a new, uncontrolled orbit. Too steep and you slam into dense air so fast that heating and deceleration tear the vehicle apart or kill the crew. That corridor is only a few kilometers thick vertically, a tiny band of acceptable entry angles and positions. You have to line that up from millions of kilometers out, after decades of tiny errors, aging sensors and limited correction fuel. There is no second try. If you get it wrong, you do not swing around and try again next week. You either bounce and lose the chance to brake safely, or you come in too hard and the mission ends in the upper atmosphere. On shorter missions, like from the Moon or low Earth orbit, the time between final course corrections and re-entry is short. The navigation solutions are fresh, the instruments are newer, and the path through space is much shorter. For a Pluto return, the entire chain is stretched. The last correction burns might still be days or weeks away from hitting the atmosphere, and they are based on instruments that have been fighting radiation, drift, and wear for decades. So you end up in a situation where navigation, which people often treat as just math, becomes a long-term reliability and fuel problem. The math says you can compute a perfect return path. Reality says your hardware, your propellant budget, and your timeline will never be perfect, and any gap between the ideal and the real stacks up over billions of kilometers. And if you do manage to solve that, if you accept the fuel costs, load up on redundant sensors, and somehow keep your guidance precise enough to hit that tiny corridor after 30 years, there is another physical enemy waiting for you that cares nothing about your math. The simple fact that space near Pluto is unimaginably cold. While your ship and your crew need to stay warm, your fuel must not freeze, and every material in your structure has to survive millions of thermal cycles without cracking apart. How do you keep a human habitat warm and stable when the natural temperature outside is so low that almost every material you know is on the edge of becoming glass brittle? Out near Pluto, in the outer Kuiper Belt region, the equilibrium temperatures are around 40 to 60 Kelvin, that is roughly minus 230 to minus 210 degrees Celsius, about minus 380 to minus 350 degrees Fahrenheit. That is not cold winter cold, that is most things behave differently cold. Your spacecraft is a tiny warm bubble in an environment that is trying to suck heat out of it all the time. At the same time, your systems are generating waste heat. From electronics, from people, from pumps, from reactors. In low Earth orbit, getting rid of heat can be the bigger problem. Out by Pluto, you are fighting on both sides. You have to keep enough heat in to protect your crew and your hardware, and you have to dump excess heat through radiators into a background that is near absolute zero. All of this depends on insulation, layers of materials that keep internal temperatures stable. Those insulating layers have to work for decades without cracking, outgassing, or letting microscopic leaks link your warm interior to the freezing outside. Multi-layer insulation, foams, seals around hatches and ports, all of that has to stay flexible, pressure-tight, and reflective after millions of tiny thermal expansions and contractions. If gaps open up, you start getting cold spots, condensation, and structural stress in places you did not plan for. On the inside, heaters become part of life support, not a comfort feature. You need to keep propellants above their freezing points, otherwise valves jam and lines block. You need to keep electronics in a moderate temperature band, not too cold or their characteristics drift and they fail, not too hot or they burn out. And you need to keep humans around 20 degrees Celsius, about 68 Fahrenheit, across living spaces, not just in one little corner. You will have condensation, mold and health problems. The farther you are from the sun, the less free heat you get, and the more your internal power plant has to work just to hold temperature. Big chunks of your power budget, from RTGs or reactors, get eaten by heaters, pumps and fans whose only job is to fight the cold. That means less surplus power for things like high-power communications, electric propulsion, or redundancy. Any underperformance in your power system forces hard choices, and thermal control is not optional. If something has to be switched off, it cannot be the heaters keeping your pipes and tanks from freezing. Now look at the propellant itself. High-performance rocket fuels, like liquid hydrogen, give you excellent specific impulse, great efficiency in terms of delta V. The problem is liquid hydrogen has to be stored at around 20 Kelvin, about minus 253 degrees Celsius, roughly minus 423 Fahrenheit. Even with very good insulation, it boils away slowly. Over a mission that lasts a few months, you can manage that. Over years, the boil-off becomes a serious loss. Over decades, it is catastrophic. You simply will not have much left. That is why long-duration missions tend to favour storable propellants, like certain hypergolic mixes, which are liquids at room temperature or moderate cooling. They are lower efficiency, you get less delta V per kilogram of fuel, but at least they do not vanish into space over time. For a Pluto round trip, trying to preserve huge amounts of cryogenic propellant for a return burn 15 or 20 years after launch is, with today's technology, basically fantasy. You would need active refrigeration running flawlessly for decades, plus perfect insulation, and you're still paying an enormous power and mass cost to babysit that fuel the entire time. If you accept storable propellants instead, your engine performance drops. That means you need more mass in fuel to get the same speed change. More fuel means bigger tanks, bigger structure, more insulation, more surface area to manage thermally. Again, the thermal problem loops back into the rocket equation. Every step you take to protect your propellants and keep them usable feeds back into mass and complexity. Then there is thermal cycling, the slow stress that never stops. As your ship rotates, different surfaces move in and out of sunlight. Internal systems turn on and off, dumping heat into local areas and then cooling again. Your orbit orientation changes with respect to the sun. Even inside, you get hot and cold spots as equipment runs and rests. Every time something heats up, it expands a little. Every time it cools, it contracts. Metals stretch and shrink, seals flex, solder joints and circuit boards bend a tiny bit. Over a mission of a few years, you design for this and hope your safety margins are enough. Over 30 or 40 years, you are looking at millions of these cycles. Metals fatigue, microscopic cracks grow, seals slowly lose elasticity and start to leak. Solder joints can literally crack, creating intermittent failures in electronic boards. A radiator line might develop a tiny leak. A structural member might weaken. An insulated cable might break internally. Any one of those failures would be annoying on a short mission, but probably fixable with spares. On a Pluto mission, a failure in the wrong system at the wrong time can end everything. A cracked line in a propellant feed, a failed valve in a cooling loop for your reactor, a leak in a key air duct, or a degraded seal in a pressure bulkhead can turn "we are coming home" into "we are just drifting now" until the system die. You go from active ship to dead hulk, simply because the thermal environment over decades slowly tore your machine apart. So you are stuck in a harsh trade, more robust materials, thicker structures, more redundancy in thermal systems. All of that adds mass, and the extra mass makes the propulsion problem worse. Cut mass too aggressively, and you get lightweight systems that may not survive the thermal abuse for 30 plus years. And even if you somehow balance all of this, even if your ship stays warm where it needs to, cold where it needs to, and structurally sound the whole time, you still depend on one fragile link to Earth, a communication system that has to work across billions of kilometers, with hours of delay and zero tolerance for going silent at the wrong moment. So what happens to a return from Pluto plan when you realise that if you lose that link, your chance of guiding a precise, safe comeback basically drops to zero? How do you run a mission when every question you send to Earth comes back as an answer almost a full workday later, while your ship is still moving at tens of thousands of kilometers per hour? At Pluto distances, around 5 billion kilometers out, light itself needs roughly 4.6 hours to travel one way. So a radio signal moving at light speed also takes around 4.6 hours to leave Earth and reach your ship, then another 4.6 hours for your reply to get back. One simple question-answer loop is close to 9 or 10 hours. There is no real-time back and forth, no "Houston, we have a problem," followed by a quick brainstorm and step-by-step coaching. That means you, on the ship, have to solve almost everything locally. If a valve misbehaves, if a sensor glitches, if guidance starts throwing strange numbers, you log it, you adapt, you move on, and maybe you send a report home later. By the time any advice comes back, the situation you are asking about is old news. For small issues, that is just annoying. For big ones, like engine burns, navigation changes, or life support anomalies, that delay means Earth cannot catch you in the act and say, "Stop, this is wrong," before the damage happens. On top of the time delay, you are also dealing with low data rates. New Horizons at Pluto distance was transmitting data back to Earth at just a few kilobits per second. That is slower than an old dial-up modem. A crewed ship would need more bandwidth, sure, but the same basic physics applies. The signal spreads out as it travels, following that inverse square law again. By the time it hits Earth, the power is extremely diluted. To get anything useful through that soup of noise, you need very large, precisely aimed antennas on both ends. Big dishes on the ship, big dishes in Earth's deep space network. You can boost power, you can use clever encoding, but you're still not getting anything close to what you think of as normal internet speeds. You will not be streaming live high-definition video calls from Pluto. You will be compressing data, choosing what to send, and living with the fact that some detailed diagnostics and high-volume logs may never make it back. So you lean heavily on autonomy. The ship's onboard computers and the crew must make the big calls. When to start a course correction, when to trim it, when to abort a burn because something looks wrong, how to respond when a reactor parameter drifts out of range, how to reconfigure power after a partial failure, how to reroute cooling if a loop is compromised. You cannot wait 9 hours to ask, "Is this okay?" You either act or you don't, in the moment, with incomplete data. That autonomy is powerful, but it cuts both ways. A bad decision by the onboard AI or by the human crew under stress can waste propellant in a way that cannot be undone. A mistimed burn or a wrong assumption about a sensor error can put you onto a trajectory that requires more delta V to correct than you have left. In a system this tightly constrained, you do not need many bad calls. 1 or 2 major missteps can push the mission from barely feasible into "we cannot make it back with the fuel we have." You might try to protect against that with more training, better simulations, more conservative rules, but over 20 to 30 years, conditions will change in ways your training did not cover. Hardware will age, software will behave differently as it runs through updates and patches, the crew will not be the same people, physically or mentally, as the ones who launched. Yet the requirement for good judgment stays just as sharp or sharper than on day one. Then there is the worst-case communication scenario, losing the link. A comms failure at Pluto is not like dropping a phone call. If you lose contact with Earth for good, even while your ship is still technically working, the mission is effectively over as a controlled round trip. You can continue to live on board, you can keep life support running, but you are now flying blind in a navigation sense. Without updated ephemerides, the precise data on where Earth, the planets, and other bodies will be when your trajectory planning gets worse over time. You cannot upload new software patches to fix bugs or adapt to failing hardware. You cannot coordinate your Earth arrival timing with ground-based systems. You cannot fine-tune your flight path to match re-entry windows or safe landing zones. The incredibly precise choreography needed to hit that tiny atmospheric corridor at the right angle, and speed becomes guesswork. Yes, the ship can carry some preloaded ephemeris data and backup procedures, but over 20 or 30 years, the accuracy of those predictions drifts. You normally depend on ground-based tracking and updated models to keep everything tight. Without that, every small velocity error, every tiny clock drift, every uncorrected perturbation adds up. You might still intersect Earth's orbit, but not at the right place, not at the right time, not with the right angle and constraints that human re-entry really needs. You could try to design a fully independent navigation system that never needs Earth, using star trackers and onboard processing to keep ephemerides fresh. But that adds yet another layer of complexity, more software, more processing power, more chances for subtle bugs that only show up when you are years from home. So communication is not just about sending pretty pictures or status updates. It is part of the control loop that lets a mission adjust to reality. When the light time delay is measured in hours and the bandwidth is measured in kilobits per second, that control loop becomes slow, fragile, and heavily dependent on autonomy that must not make big mistakes. Strip that link away completely, and the return part of the mission drops from barely possible to almost fantasy. And this brings up the next harsh layer of the problem. Even if you keep the link, even if the guidance and timing are perfect, the whole path to and from Pluto hangs on a small set of launch windows and planetary alignments that do not care about your schedule, your budget, or your crew. If you miss them, or if funding cuts delay you, the orbital mechanics themselves start pushing you toward a one-way profile. So what happens when you put all of this into the time map of the solar system, and you discover that even the best shot at leaving and the coming back is locked inside rare, unforgiving windows that can slip away for years at a time? How do you do a round trip to Pluto when the solar system only gives you a few narrow launch slots at specific decades and does not care at all whether your crew or your budget are ready? To move between orbits with minimum energy, you usually use something close to a Hohmann transfer, an efficient curved path that touches the orbit of your starting planet at one end and the orbit of your target at the other. That only works well when the two worlds line up just right. For Earth and Pluto, that just right is rare, because Pluto's orbit is big, tilted, and stretched. For New Horizons, the sweet spot came in 2006, using a Jupiter flyby to boost the probe without extra fuel. If that window had been missed, the next equally good chance would have been years away, and the alternatives would have needed more energy, more time, or both. That is for a simple one-way flyby. For a crewed ship, where your Delta-V budget is already strained, you care even more about hitting those minimal energy transfer windows. Miss them and your travel time climbs, your fuel demands climb, your radiation exposure climbs, your life support needs climb. Every slip in schedule makes the mission heavier and riskier. Orbital mechanics does not flex because your rocket development is running late, or because Parliament did not vote the money this year. Then there is the trap almost nobody mentions at first. The outbound and inbound paths are not mirrors of each other. You cannot just say, we will launch in year X, arrive in year X plus 10, then launch back in X plus 12 and get home in X plus 22. Pluto does not sit there waiting, it crawls along a 248-year orbit. Jupiter, Saturn and Neptune, which you might want for gravity assist, are also in completely different places by the time you're ready to return. Your perfect outbound geometry, the nice chain of Earth to Jupiter to Pluto, that saves you fuel and time, might have no clean reverse option within a reasonable window. When you're finally thinking about leaving Pluto, the lineup could be terrible. Jupiter might be on the wrong side of the Sun, Saturn might be useless for a helpful flyby, Neptune might be badly placed. The low-energy corridor you use as going out simply does not exist in the other direction at the time you need it. That leaves you with ugly choices. You can wait at Pluto for years, maybe a decade or more, until a decent return window opens, which stretches the mission length from already insane into career plus retirement. Or you can brute force a return on a less efficient path, burning more Delta-V, which calls for more propellant than your mass budget probably allows. Either you pay with time or you pay with fuel, and both currencies are already in short supply. Now overlay that with how human space programs actually work. Right now, agencies have trouble keeping large programs stable over 10 to 15 years. The ISS, Artemis, Mars plans, all of them are constantly being re-argued, refunded, rescoped. Priorities change, economies crash, new crises show up. A Pluto round trip is not a decade program. It is a 30 to 40-year commitment that crosses multiple administrations, multiple generations of engineers and managers. To make a human Pluto round trip even slightly realistic, you need long-term funding that never collapses, international cooperation that never fractures, an institutional memory that survives retirements, company closures, and shifting industrial bases. Every time leadership changes, someone has to resist the temptation to cancel an expensive, slow, high-risk mission that still has 15 or 20 years left before it even comes home. The practical probability of carrying a single coherent plan through all of that without fatal cuts or redesigns is extremely low. For the crew, that instability is not just a budget line, it is their lives. They would be betting that the civilization that launched them will still be willing and able to support them decades later, still running tracking stations, still updating navigation data, still listening for their signal, still ready to pay for recovery and reintegration when they return. When you put all of this together, the physics, the launch windows, the gravity assists, the timing of orbits, and the way human institutions actually behave, one pattern stands out. The only mission profiles that look even slightly sane with near-future technology are one-way in practice. You launch once, you arrive once, you maybe land or build a small outpost, and you never seriously plan to bring the crew back to Earth. You might send data back, you might send robot helpers later, but the people who go, knowing this is where their life ends. For a robotic probe, that is fine, that is exactly what we already do. We happily fire machines into the outer dark with no expectation of return. For a human mission, that is a very different ethical problem. You're not just asking for money and engineering effort, you're asking society to accept sending a small group of people on a journey that they will almost certainly never come back from, and to keep paying for them and listening to them for decades with no direct economic return. So even if you ignore radiation and life support and navigation and thermal problems, the orbital mechanics and the reality of human institutions already push you toward a brutal conclusion. The solar system might technically allow a round trip to Pluto, but the way the windows fall make that round trip almost a fantasy. Which raises the next hard question. Even if some team somehow solves every physics and engineering problem on paper, who is actually going to pay for a mission that eats budgets for generations, when there are cheaper, closer, more profitable targets everywhere inside of Pluto's orbit? How do you convince an entire planet to spend more money bringing 4 people back from Pluto than it has ever spent on any other space project, for a mission that takes decades and has no clear payoff? Look at what we already know we can barely afford. The Apollo program, if you convert it into today's money, lands somewhere around $150 to $200 billion. That was to send a handful of crews to the moon, about 400,000 kilometers away, roughly 250,000 miles, over a few intense years. Artemis, just to go back to the moon with more modern hardware, is adding tens of billions more, and that is still only a cislunar project. These are already some of the most expensive things humanity has ever done. Pluto sits more than 10,000 times farther away than the moon. Distance does not scale cost in a straight line, but once you include all the extra mass, propulsion, life support, shielding and mission duration, you're absolutely not in hundreds of billions territory anymore. You're staring at a serious human round trip that lives in the multi-trillion-dollar range, at least on any realistic architecture. And that is not counting the failed starts, the test flights, the prototypes that do not work, and the inevitable redesigns after the first surprises. And that leads to the next hit. A Pluto round trip is not just one big rocket. To even get close, you need infrastructure first, on a scale we have never built for space. Start listing it. You need a heavy lift fleet, not one giant rocket that flies once a year. but a whole lineup of vehicles that can throw hundreds of tons into low Earth orbit over and over to assemble the ship, its fuel, its shielding and its life support modules. You need orbital construction yards, real ones, with robotic arms, human crews or both, able to weld, bolt, test and repair structures that make the ISS look like a small outpost. You need fuel depots, large tanks, either in Earth orbit, cislunar space or even parked near Jupiter to support refueling and staging maneuvers. Those depots themselves need launches, tankers and maintenance. On top of that, you almost certainly need to test high-power nuclear or advanced propulsion systems, maybe nuclear thermal rockets or early fusion concepts, which means design programs, test stands, safety systems, and a fight over launching nuclear reactors and exotic engines from Earth. None of this looks like a single mission. It looks like a civilization-level project, something you build in layers over decades. The same way we built global internet infrastructure or international aviation. You're not just funding a ship, you're funding an entire deep space economy, and then using it once to send a small crew to Pluto and back. Now think about everything else you could do with that scale of money and hardware. Every dollar you lock into Pluto is a dollar you are not putting into Mars settlements, lunar mining and industry, planetary defense systems against asteroids, climate monitoring networks, or asteroid mining ventures that might actually make money. It is money not spent on near-Earth infrastructure that could support thousands of satellites, stations, and commercial platforms. From a cold policy standpoint, a one-off, multi-decade Pluto round trip looks bad on paper. It risks a small crew, it ties up heavy hardware and skilled teams for 30 or 40 years, it gives no immediate economic return, and it competes directly with projects that have clearer benefits. A Mars program can be sold as a step toward permanent settlement, resource use and long-term survival. A lunar economy can be sold as a way to support everything else in space. A Pluto round trip is very hard to justify outside of pure exploration pride. That is why when decision makers hear multi-trillion and multi-decade and no direct payoff, the veto instinct is strong. Even people who love space have to weigh this against schools, healthcare, energy, and all the other things voters care about. When budgets get cut, a 40-year deep space prestige mission is the first thing on the chopping block. This is where impossible quietly changes meaning. Physics does not forbid a Pluto round trip. The equations, on paper, let you draw a trajectory, size a reactor, and compute the fuel. But the real world is not just math. It is budgets, elections, risk tolerance, and public attention spans. If no government, no coalition, and no group of private companies is willing to put up the money for the launchers, the depots, the ship, the plutonium, the reactors, the crews, and the 40 years of operations and tracking, then the mission does not happen. In that sense, we cannot return from Pluto is really no one on Earth is going to spend what it takes to guarantee a return from Pluto. The cost to do it safely with real margins is so high that it pushes the mission out of the zone of hard but fundable and into fantasy slide in a presentation. And even if someone did say yes, even if some future alliance decided to bite down and pay, the natural next question would be, can we lower the physics burden with better technology, with fusion drives, beamed power, or radical new propulsion, so that the price and the risk do not look insane? But when you follow that thought all the way through, you start to see another pattern. Even with much better engines, Pluto still wants to be a one-way frontier. How far into the future do you have to push technology before a round trip to Pluto stops looking like a one-way bet? And even then, does it actually fix the core problem or just move it? Start with the optimistic version. Say you have fusion drives that actually work, not in a physics paper, but as hardware, flying on a launch pad. Exhaust velocities in the tens of kilometers per second, far beyond chemical engines. Now your rocket can throw out reaction mass so fast that you get big delta V with much less fuel. Travel times drop from a decade to a few years, maybe even down toward 1 or 2 years each way if you push hard. Your fuel stacks shrink, your mass ratios become friendlier and the rocket equation hurts less. Or go even further and hand yourself antimatter engines. In principle, annihilating matter and antimatter gives you insane energy density. Compared to hydrogen and oxygen, it makes a Saturn V look like a firework. On paper, this slashes your propellant needs, lets you build smaller vehicles, and gives you more headroom for shielding, life support, and redundancy. But once you give yourself that kind of engine, you do not get to relax, you just move into a different kind of hard. The bottlenecks become materials that can survive the heat and particle flux from fusion exhaust, control systems that can keep a fusion plasma stable for years, containment and safety systems for antimatter that cannot ever fail. Your big problem stops being, we do not have enough delta V, and becomes, we are putting people next to star-level power sources and asking the hardware not to screw up for decades. A fusion reactor on Earth is already hard to keep quiet and controlled in a building with constant maintenance. Shrink that down, stick it on a ship, run it continuously through radiation, vibration, and thermal cycling, and you have a whole new reliability challenge. Any serious failure becomes catastrophic, not just for the mission, but for the people sitting a few meters away from the reactor. So yes, fusion or antimatter could, in theory, help with speed and fuel, but they crank up risk and engineering difficulty in new directions that we are nowhere near solving in practice. Then there is the external power idea, beamed propulsion. You keep the heavy power sources at home, on or near Earth, and you push the ship with energy from afar. With laser sails or microwave sails, a powerful ground or orbital station fires a beam at a big reflective or absorptive sail, and the ship accelerates without carrying its fuel. In principle, you can reach high speeds this way with a light vehicle. For an outbound run to Pluto, that sounds appealing. A massive laser array near Earth drives your sail outward, you cut the beam once you have the speed you want, and you coast. The catch is braking and coming back. To slow down at Pluto, you either need a matching beaming system out there, maybe a second laser array in deep space, or you need a clever sail design that can use the sun's light or some kind of magnetic drag to brake efficiently. Right now, those ideas are theoretical and do not give you the kind of tight control you need for a human ship. For the return leg, the problem is even worse. You would need either a giant beaming system already deployed in the outer solar system to hit your sail inward, or some reversible setup where the same sail and beam geometry can serve both directions with good efficiency and safety. That means building deep space power stations and precision optics at Pluto distances before you ever send people. It quickly starts looking more reasonable for probes than for crews. Robots do not care if braking takes longer, or if a failed beam sequence leaves them drifting. Humans do. This pushes you toward a different mental model, where going to Pluto does not necessarily mean moving a human body all the way out and all the way back through 10 billion kilometers of vacuum. You start thinking about telepresence robotic avatars, or, further out on the speculation curve, some form of mind upload or partial neural model. In that frame, you might stay on or near Earth, in a safe environment, while your robots operate on Pluto with high autonomy. They send back data, video, haptic feedback. You remote drive them with a delay, or you let onboard AI handle low-level tasks and you direct the bigger actions. The return is not the body, it is the data. The experience is the science. The signal crosses space, not the flesh. Even the wilder concepts, where some pattern of your mind is copied or extended and sent out as software, still fit that pattern. What comes back is information, not a human nervous system that has survived decades of radiation, isolation, and mechanical risk. In simple terms, it is far more plausible to send representations of you to Pluto and back than it is to send your actual body there and back. So when you add the future tech layer on top of everything else you have already walked through, the picture does not flip the way you might hope. Distance is still huge, delta V requirements are still harsh. The rocket equation is softened by better engines, but not erased. Radiation still accumulates. Life support still has to run for absurd lengths of time. Navigation still demands precision over billions of kilometers. Power systems still need to survive decades. Budgets still have to stay stable for generations. Put it all together: distance, speed, fuel, radiation, human biology, reliability, navigation, heat management, communication delays, orbital windows, and money. None of these alone says this is strictly forbidden. But together, they build one clear story with anything even close to current or near-future technology. Sending humans to Pluto is, in practice, a one-way move. You can get there. You can land, build habitats, send back terabytes of data and video, talk to Earth on a multi-hour delay. You can do science, you can plant flags, you can live and die there. What you almost certainly cannot do, not with the tech curves and behaviour we actually see, is guarantee a safe, controlled, high-probability return for those same humans. The equations might allow it. The hardware, the biology, and the civilization behind them do not. So when someone says, "Why is it impossible to return from a trip to Pluto?" the honest answer is, it is not that nature blocks the path. It is that every part of the path is balanced on the edge of what we can do. And when you chain them all together, the mission crosses from heroic and hard into no one is actually going to build this. You can go to Pluto, you can send your instruments back, but you, the traveller, are stepping through a door that for now only swings one way. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.